Okay, welcome everyone to the 97th meeting of New Directions in Group Theory and Triangulated Categories. Today our speaker is Vashaw from the MIT, and he'll be speaking to us about a Chinese remainder theorem and Carlson's theorem for monoidal triangulated categories.
Yeah, great. Let me just... Oops, sorry, that's the wrong screen. There we go. Okay, great. You can see this fine?
Yeah.
Yes.
Okay.
Yes.
Perfect. Great. Yeah, so thanks for the introduction. Thanks for this this opportunity to speak. So I'm going to be talking about some joint work with Dan Nakano and Milan Yakimov. So let me start with some setup. So in this talk, K is always going to be just an algebraically closed field. All categories are going to be assumed to be linear over this field. T throughout the talk is going to be a finite tensor category. These are going to be the main objects of study. So just as a quick reminder, this means that we have a monoidal product. It's bilinear. The Hom spaces are all finite dimensional. Objects are all finite length. The unit object is simple. We have finitely many simples. We have enough projectives, and we have every object has a left and a right dual. And another way to package this information, of course, is just to say that, at least the finiteness conditions, a way to package this is to say that it is equivalent to modules for some finite dimensional algebra. So a lot of the talk will be focused on finite tensor categories, but some of the results will be stated in wider generality for monoidal triangulated categories. So in that case, I'll usually denote this by K. Of course, I'll have no assumption of any kind of symmetric or braided structure. So I'll never be assuming that A tensor B is isomorphic to B tensor A, even object-wise isomorphisms. I'm not assuming that they exist. And probably for most of the results that I'm going to say, I think everything here was already known in the symmetric situation by work of Balmer and Balmer-Favi. So I might not provide references after every theorem for the commutative case, but just as a disclaimer at the start, if you're looking for these results in the commutative case, you can find them in previous work of Balmer. Right, so for simplicity, all the categories in this talk, I'm assuming are rigid, so including the monoidal triangulated categories. So I'm assuming that objects all have left and right duals. And of course, one will just denote the tensor unit. Okay, so in general, what we want to study are support theories for tensor categories and for monoidal triangulated categories. So what is a support theory? So a support theory is just a way of assigning to every object of the category some closed subset. So here I'm denoting the support theory by sigma. So sigma takes in an object, say A, in the category, and it outputs some closed subset of a geometric space. And of course, we don't want to just assign closed subsets of topological spaces completely randomly, we want to assign them in a way that respects the structure of the category. So in particular, respects the homological structure and the tensor structure of T. So of course, there are many different ways of doing this. And the two that we're going to be focused on in this talk are the cohomological support and the Balmer support. And I'll denote these by W and V respectively. And I'll say a little bit more about both of these. I think there are probably some experts in the audience for whom I'm going to say some things that you probably already know, but so bear with me. At the very least, I want to say it in order to just set the notation that I'll use later. So of course, one of the ways in which we mean respecting the homological properties of T, one of the things that falls under this umbrella is projectivity detection, which means that if our support variety, our support theory, sends an object to the empty set, this should happen if and only if the object is projective. And another way of saying that, I mean, this means kind of formally that the support theory is well defined both on the level of the original abelian finite tensor category, but also on the level of the stable category. So stable category I'll denote by underline T. This is a category where objects are the same as in T, but morphism spaces we factor out by those morphisms which factor through projectives. So in this category, in this new stable category, an object is isomorphic to 0 if and only if it was projective in the original category. In general, so using properties of dual objects, one can check that a finite tensor category is Frobenius. So projectives and injectives coincide. And this means that the stable category is triangulated. And the tensor product is still well defined on the stable category. Okay, so this stable category of T is our prototypical example of a monoidal triangulated category and is one of the main examples that we're interested in studying. Of course, like I said, some of the results I'll state for more general monoidal triangulated categories, but this is kind of the one at the moment that we're most interested in studying. Okay, so what's kind of the big picture? So of course we want to understand our tensor category T or the stable category T underline. And our first goal that we could possibly give is, well, we might want to classify all the indecomposable objects of the category. And then, so classify the indecomposables and then understand how they tensor together. So in some sense, what that would mean is you understand everything about the category. Unfortunately, or fortunately, depending on your opinion, this is not possible in even some very basic cases. So even for some of the first finite groups you might think of, these are wild representation type. So it's completely impossible to classify the indecomposable objects. So the point is we need to replace this original goal. So the original goal of kind of classifying all of the indecomposables and seeing how they tensor together. Well, we need to replace this with a goal that's more tractable. So one way of doing this is to instead try to classify the thick ideals. That is, collections of objects which are triangulated, closed under direct summands, and closed under tensor product with arbitrary objects. So instead of classifying all of the indecomposables, we try to classify thick ideals, which in some sense means classifying the indecomposables up to some suitable notion of equivalence, where equivalence means you can generate one indecomposable from another by repeated application of these operations. A second major goal, right, that we're interested in is, well, I still haven't recalled what the cohomological support is and what the Balmer support is, but I'll recall these in a second. And these are two natural support theories that we have defined on any finite tensor category. And so a basic goal that we're interested in doing is, well, what is the relationship of these two supports to each other? Okay, so let me recall both of these two support theories. So in order to construct cohomological support, we need to recall the Yoneda product. So this is true just in any abelian category. We have a product that goes x to I a b across x j c a to x to I plus j c b. The point is, of course, we can represent an homogeneous element of x as a x to I as an I-fold extension. So For the first X group, we have an I-fold extension that begins at B and ends at A. For the second X group, we have a J-fold extension, which begins at A and ends at C. And of course, the point is we can just splice these two exact sequences together at the A copy and get an I plus J fold extension, which begins at B and ends at C. So here, using this Yoneda product, if we collect all of the xi of AA together, so that I'll refer to that as X bullet, so it just means the direct sum of all the xi's, then this gets the structure of an associative algebra under this product, a graded associative algebra. And each xed AB becomes a bimodule, so xed AA acts on the right and xed BB acts on the left. So this is true, that previous slide is true in any abelian category. Now for finite tensor category, we have this particular object 1, the tensor unit. And from this, we get two different ring homomorphisms from the x of the unit object to x of AA for any object A. The point here is that the tensor product is bi-exact. So we can start with an I-fold extension, which begins and ends at 1, and just tensor every term in that extension by A on either the left or the right. And in either case, we get an extension which begins and ends at A. So you could use either of these ring homomorphisms in order to define support varieties. I mean, in order to be consistent, you should define one at the beginning. So I don't think it'll play a role in this talk which one we use. Either one is fine for the purpose of defining support varieties. Okay, so now we can say what is cohomological support. So here, I of A. So now I have this ring homomorphism by which each xed AA becomes a module for xed 1, 1. So I have some annihilator ideal for xed AA in xed 1, 1. So I'll denote that by I of A. Then the cohomological support of A is just going to be the Zariski closed subset of proj of the cohomology ring defined by this annihilator ideal. So that is all of these homogeneous primes which contain the annihilator ideal. So this is some closed subset of the proj of the cohomology ring. And this was, this has kind of a long history, right? This originally came out of work that was being done by Quillen, Dade, Carlson, Evrunen, Scott, Alperin, Evans, Benson, Carlson, Ricard, many other people. So, and it was originally being done in the context of modular representation theory for finite groups. But you can make the same theory in kind of broad generality. So the same support theory one can define for arbitrary finite tensor categories. And it has been studied in that context more recently. Okay, so I've now told you what is the cohomological support for our finite tensor category. So now I should recall the other major player, which is the Balmer support. So, of course, this is constructed, I mean, it can be constructed for any monoidal triangulated category. So recall that a thick ideal is just going to be some subcategory, some full subcategory, okay, so these first two conditions are that it's triangulated, so it's closed under shift and shift inverse. It's closed under this 2 out of 3 property with distinguished triangles. Then it's also thick, which just means if you have a direct sum, which is in this ideal, then both summands are also in the ideal. And then, of course, so if we stop there, it would be a thick subcategory. In order to make it a thick ideal, then we also require that it's closed under tensor product on the left and on the right by arbitrary objects in the category. And of course, another way of conceptualizing this, right? An ideal for a ring is just the same thing as a kernel of a ring homomorphism. And the point is, well, this definition it's defined in this way because this is precisely just the kernel of a monoidal triangulated functor. So if you have a monoidal triangulated functor between two monoidal triangulated categories, the collection of objects which are isomorphic to zero after applying this functor is a thick ideal. And every thick ideal appears in this way. Okay, so now we can define the Balmer spectrum. So of course, this is comes originally due to work of Balmer, 2005 in the symmetric case. I'll write down here, I'll just recall the natural non-commutative analogs of Balmer's definitions. So the Balmer spectrum is just going to be the collection of prime ideals, that is, thick ideals which satisfy the prime condition on the level of thick ideals. So if you have two thick ideals, I and J, and I tensor J is contained in P, then the requirement is that either I or J is contained in P. Equivalently, you can also write down this condition, kind of a more object theoretic definition, which is that A tensor K tensor B. So you have to put an arbitrary object kind of in the middle of A and B. If this subset of objects is all contained in P, then this should necessitate either A or B is in P. And then if K is symmetric or braided, then an equivalent condition is completely prime. For general non-commutative case, of course, completely prime is a stronger condition. So a completely prime ideal implies that it's a prime ideal, but not the other way around. And so the completely prime condition is just the usual prime condition that you think of from commutative rings. So A tensor B is contained in P implies that A or B is in P. Okay, so we have two kind of guiding philosophies at this point. The first is one should treat a monoidal category, triangulated category, like a ring. So this is, I think of this as one of Balmer's kind of original foundational insights, which was integral to this starting this field of tensor triangular geometry, which was that defining this prime ideal, right? You essentially just write down the definition of a prime ideal of a commutative ring, and it turns out that this is useful. And the second guiding philosophy is that categorical properties of K should reflect topological properties in the Balmer spectrum. So these are kind of the two guiding philosophies that I want to think of as motivating the main results that I'm going to say in this talk. Right. So I still haven't told you what the Balmer support is. And really, I've only told you what the Balmer spectrum is as a set. Of course, it also has a structure as a topological space. Closed sets are going to just be V of A. So I call this the Balmer support of A. And this is defined to be those prime ideals which A is not in. So this generates the closed set on the Balmer spectrum. A general closed set looks like some intersection of the Balmer supports of objects. We have this related map, which I'll denote by phi, or maybe phi sub v. This takes in a collection of objects S and outputs the union of the Balmer supports of all objects, which gives, well, if S is infinite, this might not be a closed set anymore, but instead it's a specialization closed set, so a union of closed sets. So what is the use of the Balmer spectrum? So in some sense, the Balmer spectrum is a formal topological space which is built for the purpose of classifying thick ideals. And this is one of kind of the very original motivations in Balmer's paper. So the theorem that Balmer proves in 2005 is, in the case where K is symmetric, we have a bijection between the Thomason closed subsets of the Balmer spectrum and the thick ideals of the category. So this is kind of one of the foundational theorems that all of tensor triangular geometry is built on. And there's recently been kind of a flurry of activity regarding this theorem in the non-commutative case. So in general, it's not true. So we've constructed counterexamples. I mean, we've constructed examples of non-commutative monoidal triangulated categories where there is not a bijection between Thomason closed subsets of the Balmer spectrum and thick ideals. But in many specific cases, it is true. So in particular, if all prime ideals are completely prime, then this was proved by Malik and Ray. It was proved by James Rowe that this works as long as the Balmer spectrum is Noetherian. And then it was proved by in joint work with Dan Nakano and Milan Yakimov that this theorem also goes through as long as you have a thick generator for the category. So as long as there exists a single object such that the smallest thick subcategory containing that object is the whole category. So in particular, this is true for our main example that we want to study, which is stable categories of finite tensor categories. Because in that case, you can take, of course, as the thick generator, you can take the direct sum of the simple objects. So since we have a Jordan-Holder theorem, the smallest thick subcategory containing the direct sum of the simple objects is the whole category. We have a thick generator, so we have a bijection between Thomason closed subsets and thick ideals. Right, and so I have some counterexamples in this joint work with Hongdi Huang, where I mean, of course, by necessity, it fails all of these conditions. So it's a non-commutative monoidal triangulated category where you have non-completely prime ideals. It's non-Noetherian spectrum, and it doesn't have a thick generator. And so we don't have I mean, we can prove that there's not a bijection between the Thomason closed subsets and thick ideals. Right, so I said at the beginning of the talk, of course, that I'm assuming that all categories in this talk are rigid. So if I didn't have a rigidity assumption, you still have a theorem that's similar to this, but you no longer get a bijection with the thick ideals. Instead, you might have to say semi-prime or radical thick ideals. But yeah, let me not dwell on that. Yeah.
So regarding these non-examples, you just said the spectrum is not Noetherian in those cases. How, like, is it still a good-looking spectrum from some other angles, or is it completely pathological?
Yeah, so I guess whether or not you think it's completely pathological is, I guess, a matter of opinion.
Sure.
But so I can say what it is. So the spectrum is, so you can construct this by taking some kind of group action on some monoidal triangulated category whose spectrum you understand. Then you can build the cross product category using this group action. So in order to actually construct an example, you need if you start with a category which has a thick generator, then the group should be infinite so that the cross product no longer has a thick generator. Then what is the spectrum of this cross product category? So it's something like the quotient of the original spectrum by the induced action of the group. except that you take, so usually closed subsets in a topological quotient by a group action are the closed orbits. In this case, you take not just closed orbits, but all orbits of closed sets become the closed subsets of the Balmer spectrum of this cross product category. So I mean, in some sense, you can still say what the Balmer spectrum is. It's not so pathological that it's like you can't understand it or say what it is.
Thank you.
Yeah. Other questions at this point? Yeah. Okay. Great. Okay, and then just to say a little bit more details about this bijection. So the way the bijection works is if you have a thick ideal I of your monoidal triangulated category, you can send this to the union of all the Balmer supports of objects in the category. This is a Thomason closed subset. And then to go the other direction, starting from a Thomason closed subset S, you can take the collection of all objects whose support lands you in S. So these are the maps that give you a bijection. This gives it descends to a bijection if you replace the left-hand side with principal ideals, so ideals generated by a single object, and you replace the right-hand side with closed subsets, then it's still a bijection. Or another way of saying this is every closed subset of the Balmer spectrum can be realized as the Balmer support of a single object. Okay, so this bijection, we'll be using it for all of the results that we say later in the talk. So classic example, right? If you start with a topologically Noetherian scheme, you can take the perfect derived category. This is a commutative monoidal triangulated category. And then it's based on work of Thomason. One can show that the Balmer spectrum of this category is just the same thing as the scheme that you started with, X. In other words, you can reconstruct a Noetherian scheme from the data of its perfect derived category. So the other example, the other kind of motivating example is stable categories of finite groups. So here G is meant to be a finite group or maybe a finite group scheme. K is a field in characteristic P, which divides the order of the group. Then we have cohomological support, which lands in the proj of the cohomology ring. We also have the Balmer support, which lands in the Balmer spectrum. And then in this case, we have a third player, which is the rank variety support or the pi point support, which was defined respectively by Carlson and by Friedlander-Pevsova. And then by Avrun and Scott in the rank variety case and by Friedlander-Pevsova in the pi point case, these two things are isomorphic. And it's a theorem of Benson, Carlson, Ricard, Friedlander-Pevsova, and Balmer that both of these spaces coincide with the Balmer spectrum in a way that commutes with these various support maps. Okay, so we have all of these natural supports, and in the case of the stable category of a finite group, they're all secretly the same support. I mean, they all coincide. Why is this such a fantastic theorem? So, I mean, many of these, like I mentioned earlier, I mean, you can write down very simple groups like Z3 cross Z3, whose indecomposables are not able to be classified. But what we are doing, I mean, what we can do with this theorem is classify the indecomposables up to this notion of equivalence. And this gives you kind of a computational tool. So if I want to say, if you hand me two indecomposables and you say, okay, here are two indecomposables A and B, and I want you to say, can you generate A from B in the triangulated category? Then all I have to do is compute their cohomological supports or rank supports and see if there's a containment of one support variety in the other. And then that tells me, can I generate one object from the other by these triangulated category operations? So one thing that's our motivation at this point is, well, how do we generalize this to arbitrary finite tensor categories? In this case, now we still have the cohomological support, we still have the Balmer support, and it would be natural to wonder, well, does this Friedlander-Pevsova theorem just carry over to the case of finite tensor categories? But the problem is we know examples where it's not true, where we don't have the cohomological support and the Balmer support coinciding. So this motivates this next definition that I want to say. So the categorical center of the cohomology ring of so I'll define this in just the case of a stable category of a finite tensor category. So this, I'll define this as the subalgebra of the cohomology ring generated by those elements G such that we have a commutative diagram. So here, if I have G in the cohomology ring, I can, and it's a homogeneous element of the cohomology ring, I can really think about this G just as a morphism in the stable category from 1 to a shift I of 1. And so this diagram commuting means, well, if I tensor this morphism by the identity of any simple object M, it should coincide with tensor on the other side by identity M under these structural isomorphisms that are part of the data of a monoidal triangulated category. Okay. So I pick up all of those morphisms in the cohomology ring, which in some sense tensor commute with identity morphisms of simple objects. And I declare this subalgebra to be the categorical center C. Okay, so now we have some subalgebra of the cohomology ring. Of course, we can define support varieties relative to this subalgebra too. So I'm just kind of repeating the definition of cohomological support from earlier. So I pick up just the Zariski closed subset of the proj of the categorical center defined by the annihilator ideal of X to AA. And based on the examples we have, we conjecture that, okay, so the Balmer support doesn't correspond to the general cohomological support, but maybe it corresponds to this central cohomological support. Okay, so this is the conjecture. So some examples where this conjecture is known. So of course, it's known in these cases that I already said. So Benson, Carlson, Ricard, and Friedlander, Pevsova. In both of those cases, the category is symmetric. So the categorical center is just the whole cohomology ring. It's also known in the case of finite dimensional commutative Hopf algebras by work of Negron-Pevsova. We've proved it in the case of these Benson-Witherspoon and Plavnik-Witherspoon smash coproduct Hopf algebras, which are a generalization of 3. It's also, I've also checked that it's true for Drinfeld centers of Benson-Witherspoon and Plavnik-Witherspoon smash coproduct Hopf algebras. And then a generalization of these smash coproduct Hopf algebras are cross product categories by actions of finite groups. And this is a theorem of myself with Hongdi Huang, which is related to the example I was discussing earlier, where you don't have a bijection with Thomason closed subsets. In that kind of non-example from earlier, one needs to make the group be infinite. In this theorem here, these cross product categories, I mean cross product with a action of a finite group.
Oh, Kent, I have a question. So I think Pablo Ocal announced a result where Well, I actually asked him whether he can prove the conjecture in his case. Do you know where that actually fits into 1 through 6? Does it fit under 6, for example? I think
Yeah, so I
he was
am
looking at certain twisted tensor products.
right. So I don't think I've seen I don't know exactly what his result is. I mean, I don't think there's a result out. I think I saw he gave a talk about it at some point,
Right.
and what I took from talking to him was that he was doing actions by um maybe a twisted tensor product by an action of a finite dimensional Hopf algebra,
Mhm.
which so I guess it's possible that his result would be a generalization of 6.
Okay. That makes it clear.
But I haven't seen the result, and I don't think it's posted yet. So I'm not sure. I'm not sure.
Okay. Thanks.
Sorry,
Any other questions?
I had a question. This is not related to this page, maybe, but maybe theme-wise there is a relation. So regarding like looking for analogs of things that are known for the symmetric setup, so there was this theorem in a preprint by Chang'an Zhou, Bedon Sanders' student, where he showed that if a rigidly compactly generated TT category, well, symmetric monoidal like TT category, if such a thing is stratified, he showed that the spectrum has to be Wickli-Noetherian, which is going the other way, right? Because there was this theorem by Barthel, Hart, Sanders, where they start with a Wickli-Noetherian spectrum and assume some nice support theory exists, and they show stratification. So I'm guessing from what you're saying that the immediate non-symmetric analog of this is not known to be true, right?
That's
Is that
correct.
okay?
Yeah.
Yeah.
Yeah, I think I saw the paper that you mentioned, but I haven't thought carefully about it, and
Yeah.
to the best of my knowledge, I don't know if anyone else has looked at this.
Yeah, the proof doesn't go through, I'm sure about that. But
Mhm.
yeah, okay.
Oh.
Okay, thank you.
Yeah, any other questions at this point?
I'm sorry, can I ask something else?
Yeah, sure.
If I mean, you mentioned this earlier when you were discussing the work of Malik and Ray. Shamarpita is in the audience still, I guess. Yeah, well, so this condition of all primes being completely prime,
Mhm.
I know that it's different from literally having symmetric throughout. But I mean, is it a big? I mean, I'm guessing it's a big difference, right? Like there can be lots of categories where all primes are completely prime, but still, um, you don't have commutativity like.
Yeah, there can be many categories. So I think of this list that I'm displaying on the screen, um, I mean, is that
Stable model categories over finite dimension Hopf algebras would be, I guess, an example.
Right.
so not stable categories. I mean, so it
Over
depends on the
finite
Hopf
dimensions.
algebra.
Yeah.
So for example, these Benson-Witherspoon and Plavnik-Witherspoon smash coproducts, these are finite dimensional Hopf algebras, um, where completely prime, you have prime ideals which are not completely prime.
Okay. Right. Yeah. Mm.
Um, yeah, so I think both 4 and 6 kind of give examples of this.
Because I
But
know
I
there
think
was
we
a.
also know examples. So we know examples of like small quantum group of
Okay. Yeah. Yeah. Yeah.
a
Thank you.
Burrell subalgebra.
Yeah, I don't mean to stall you for long, but isn't this the thing that Buon, Krauser, Solberg had famously gotten wrong? Well, not famously, I mean, you know what I mean.
Um,
I think I read it in one of your papers that there was a proposition in one of their
so I
papers
think
somewhere.
the proposition which we had trouble with, I think the claim was that the Balmer spectrum is functorial on non-commutative tensor triangulated categories. And that it would be functorial if all prime ideals are completely prime.
Right.
They do give a definition of prime ideal, which is not completely prime in that paper. But I think that the proposition you're referencing is had to do with the functoriality of spec.
Yeah, thank you.
Hi, Kent. Can I see the conjecture once?
Yeah, sure. Right. So the conjecture, just to say it again, we have this version of central cohomological support, which is based on the categorical center, not based on the whole cohomology ring. And the conjecture is that the Balmer spectrum of any stable category of a finite tensor category is the same thing as proj of this categorical center, in a way so that these support theories commute.
Yeah, okay. Thanks.
Great. Okay, so let me say some things about the obstacles to proving this conjecture. So in the way that I think about it, there are kind of three major obstacles. So one is that we don't know that the cohomology ring is finitely generated. So this is the meat of the Eddinghoff-Ostrich finite generation conjecture. So we need some finite generation in order to prove the conjecture. If the Eddinghoff-Ostrich conjecture is true, then it follows that each x to A is finitely generated as a module over the categorical center by applying a theorem of Negron and Plavnik. The second major obstacle is the tensor product property. So tensor product property, most people are more familiar about this in the commutative context, where it's usually stated as support variety of a tensor product is the intersection of the two support varieties. In this non-commutative case, for general monoidal triangulated categories, the property that we need is that one needs to take the union of all of the supports where you're allowed to stick any object possible in the middle of the tensor product. So it's not just the tensor product, the support of a single tensor product, it's the support, it's a union of supports. But the right-hand side should still just be the intersection of the support of A and the support of C. So this is a very difficult property to prove, and it's something one needs to check. Then the last major obstacle is extension. So one needs to check that there's kind of a well-behaved extension of this support theory to the category of all potentially infinite dimensional modules. We have at least so maybe I'll speed up a little bit because I'm starting to run low on time. So we do prove that as long as we have some finite generation conjecture, then we have a surjective map, which goes from the Balmer spectrum to the proj of the categorical center. So it's a let me say this kind of very classical theorem about support varieties. So originally proved by John Carlson in 1984. So the theorem is, I'm stating it in its generality for finite tensor categories, which is if you have a finite generation condition, then the support of any indecomposable object is connected. And there's kind of this whole history of people proving this and proving related versions of this theorem. But it kind of all comes from this original paper of Carlson. So just a summary of kind of where we're at this point in the talk. So we've conjectured that there's this close relationship between a version of cohomological support, the central cohomological support, and the Balmer support. And this condition is kind of hard to prove. We have these major obstacles to proving it in general, but at least we have a surjective map in one direction. And we have this Carlson connectedness theorem over on the side of cohomological support, which is that support of an indecomposable module is connected. Okay, so one of the main theorems that I want to say in this talk is, of course, we expect there to be a close relationship between these two support theories. We have a connectedness theorem on one side, so we expect there to be a connectedness theorem on the other side, and this is what we're able to prove. So if you have a monoidal triangulated category, we want it to be generated as a thick subcategory by a single object. We need it to be compact part of a compactly generated monoidal triangulated category. So e.g., this all applies to our main example, stable category of finite tensor category. Then the theorem is, if you have an indecomposable object A, then the Balmer support of A is connected. So there's no requirement of finite generation. There's no requirement of tensor product property. So the main remainder of the talk is to go through how we prove this. And the main way that we prove this is by the other theorem that's in the title of the talk, which is proving a generalized version of the Chinese remainder theorem. So let me say a little bit more back.
Can you back up just for a second? A quick
Yeah.
question. So in the Berg, Plavnik, Witherspoon result, do they actually have to assume finite generation for their? Oh, I see. Okay, so they do. They do assume finite generation for their connectedness theorem.
That's right.
Okay, thanks. That's all I needed.
Yeah.
Thanks. Okay.
Yeah, so let me say, in order to say how we prove this generalized Chinese remainder theorem, I'm going to need some of the tools from compactly generated monoidal triangulated categories. So again, maybe I'll go through this kind of quickly because I don't want to take another 30 minutes. So compactly generated just means generated by the compact objects. You have to have set indexed coproducts. And then we say a monoidal triangulated category is, well, yeah, we want a monoidal triangulated category which appears as the compact part of some compactly generated monoidal triangulated category. And this is true for the stable categories of finite tensor categories. So what's the payoff? Well, the payoff is we get these Ricard idempotent functors. So Brown representability says that if I have or an application of Brown representability says that if we have a thick ideal I of K, I can form the localizing category loci of K hat. K hat is the big compactly generated category. Of course, we automatically have the inclusion functor that goes from loci to K hat. And we can form a Verdier quotient, and we get a functor from K hat to K hat quotient by loci. Brown representability says that both of these functors have adjoints. And using these adjoints, we get two functors which go from K hat to K hat. So one of these is Li, the other one is gamma I. Gamma I takes value in just this localizing subcategory loci, and Li takes value in loci perp, so objects which admit no maps from loci. And for any object A, we have a distinguished triangle which goes gamma I, A to Li of A. So this is incredibly useful theorem. We think of this as kind of, it kind of allows us to split A up into the part of A that's in loci and the part of A which is perpendicular to loci. Okay, so let me state our generalized Chinese remainder theorem. So a recollection of what the standard Chinese remainder theorem is for rings. So the theorem is, if you have a collection of pairwise coprime two-sided ideals of a ring R, then there's an isomorphism R quotient by I with the product of R quotient by I sub I. And okay, here's our generalized Chinese remainder theorem. So here we need to be, our monoidal triangulated category should be the compact part of some compactly generated monoidal triangulated category. Then the theorem really looks exactly the same. So if you have a collection of thick ideals, which are pairwise coprime, so that means the pair of any pair of two of them generates the whole category K. Then we have some equivalences of monoidal triangulated categories. Well, on the compactly generated level, this is K hat quotient by the localizing ideal generated by the intersections of all of the I sub i's. And this breaks down as a direct sum of K hat quotient by loc I sub 1 up to loc I sub n. And then by taking the compact parts of both sides of this equation, we get that the idempotent completion of K quotient by an intersection of ideals is the same thing as the direct sum of the idempotent completions of K quotient by I sub 1 up to K quotient by I sub n. Okay, so maybe I'll skip the proof sketch. I mean, the point of the proof sketch, though, is just to use these Ricard idempotent functors Li and Lj, gamma I and gamma j, to break is so if you have two coprime ideals, to break down an object into Li of A plus Lj of A, and then extend this to arbitrary collections of pairwise coprime ideals by showing that if you have three coprime ideals, I1, I2, and I3, then I1 intersect I2 is still coprime to I3. And then the second part of the theorem just follows from general facts about the compact part. Yeah, so I have a typo here on the last line. So here this should read the compact part of K hat quotient by loc I. The compact part of that is the idempotent completion of K quotient by I. So now we can sketch the proof of the Carlson connectedness theorem once we already know the Chinese remainder theorem. So the point is that two ideals are going to be coprime if and only if the union of the supports of I and J are all of the Balmer spectrum. Well, the intersection of I and J is going to be empty if and only if the supports of I and J are disjoint. So this means that if we have the Balmer support of an object A, suppose it's disconnected, so you can write it as the union of two closed sets. Like we said earlier, every closed set can be written as V of B for some object B. So we're in the situation where V of A is equal to a disjoint union of V of B union V of C. Then this decomposition result says that actually A breaks down as Li of B direct sum Lj of C in the whole compactly generated category. Well, of course, that means that it has to break down as a direct sum of objects in just K, which means it's not indecomposable. So I'll say a little bit about recovering some previous results. So of course, it recovers Carlson's original theorem. It recovers a central cohomological analog of Berg-Plavnik-Witherspoon's theorem under some conditions. And I should also say that these conditions are weaker than just the conditions that say that actually Balmer support is the same as cohomological support. Of course, if you had those stronger conditions, then of course it would imply that, but under some weaker conditions, it still implies the Berg-Plavnik-Witherspoon results. So we have yeah, so maybe I'll just say kind of quickly there's some special case where the whole Balmer spectrum decomposes as a into connected components. So in this case, what the Chinese remainder theorem says is that actually the whole category itself breaks down as a direct sum, and the spectra of each thing appearing in that direct sum are the two connected components of the original Balmer spectrum. So this also kind of recovers a very basic result. So this result is easier to show, but this is just the result that if you have a disconnected scheme, then the derived category of the scheme breaks down as a direct sum of the derived categories on the two connected components of the scheme. And then I think the last example I want to say is there was also work in the late 90s and early 2000s by a number of people. So Carlson, Donovan Wheeler, Benson, Krause, who decomposed particular quotient categories. So particular idempotent completions of quotients by certain ideals that they define, which are defined in this way, this I and J. And what we were able to check is that actually these I and J, these ideals that they study, these can both be written as intersections of maximal ideals. And maximal ideals are pairwise coprime. So their results also follow from, some of their decompositions also follow from this generalized Chinese remainder theorem. Okay, so let me end there. Thanks for your time.
Thank you, Kent. We could have taken 10 more minutes. It was fine. Let's all give Kent a round of applause. I think Dan, you're muted.
I'm muted. Okay.
Okay. Any questions for the speaker? So when you have this condition that K has to be the compacts in a larger compactly generated, didn't you guys used to call it M delta C's in a larger compactly generated M delta C monoidal triangular category? Is it a very big requirement? Because like one can with stable infinity categories, one incompletes the starting small stable infinity category and then it's done. Like in this setup, is it a big requirement?
Yeah, so I don't think it's a big requirement. I think all of the examples that we're interested in satisfy this. And like you say, under some wild assumptions, like admitting a DG enhancement or admitting a stable infinity enhancement, it should be true. I'm sure one can construct some pathological example which does not have an enhancement and maybe doesn't admit a compactly generated big category that it sits in, but I don't think of that as a a difficult requirement.
And also when like in cases such as the examples looked at by you and Hongti, like when it's not exactly, do you call it stratification? Like when that bijection is absent, I'm guessing something like the tensor product property should also be absent. Is that a fact, or is this just
so you mean this, right? So you're
like in an abstract setup, if I don't have,
right, so you're okay.
Yeah.
So you're mentioning this.
Yes.
Somehow the tensor product property kind of comes for free here because you're defining it on the Balmer spectrum, which is kind of set up in order to
that's right.
formally satisfy the tensor product property. So it's an interesting example to me. It says if you don't satisfy any of these four conditions, you still have a
right.
you still have tensor product property.
I think there was a later paper also by Peter, Julia, and Sarah Berg, Klubnik, Witherspoon, with some more failures of the tensor product property. Do you know if in the examples that they look at in that paper, this bijection is present or absent?
Yeah, so this bijection is still going to be true.
Yeah,
I mean, the bijection you mean between
indeed, yeah.
the Balmer spectrum. So I think that's a good question. So let me so part of the the difference in terminology between our paper and their paper is that when they say tensor product property, they don't mean this property that I have written down here.
Oh, I see.
They mean actually WC of A
I see.
tensor C.
Sorry. Yeah, okay. Yeah, of
So
course.
the point is that, I mean, our philosophy is you need this more general tensor product property. They prove that you don't have this more restrictive tensor product property, which I would also agree that I expect.
Right.
Or another way of putting it is here. So I think the failure of the tensor product property in some sense is the failure of this isomorphism. There not being an isomorphism between the spectrum and the proj of the whole cohomology ring. So kind of the whole point of this categorical center using this particular subalgebra is to deal with the fact that it's not necessarily nicely behaved on the level of the whole cohomology ring.
Right. And final question, somewhat lighter note. So when Milan spoke last year, I think it was almost exactly a year ago, he mentioned towards the end, when I asked something stupid, I guess, that the Ettinghoff, the FG conjecture is quote unquote widely believed to be true. So do you also believe that?
Yeah, I guess I would,
because I told someone I used the phrase widely believed to be true in a conversation with, can't remember, maybe Julia Pepsova, and she said, "Is it widely believed to be true?" I think Milan said it, and then I went and checked the video, and he did say it.
Yeah, so I mean, certainly there are no known counterexamples.
Yeah, sure.
It's been conjectured for 20 years or something, and there's no counterexamples. So, whether you believe it or not,
yeah,
I guess is, certainly I haven't seen any evidence that it's not true.
Right. Yeah, sorry about the last one. Any more questions, anyone?
Yeah, so I have a few questions and comments. Actually, I was a postdoc under Eric Friedlander when they actually proved the finite generation for finite group schemes. So
I see.
it was a very exciting time because we were not sure whether it was going to work out or not, or they were not sure either. So
Friedlander Susskind, right? Okay.
yes, Friedlander Susskind. Yeah. So the first question I have, which is a more serious question, is what about the homological spectrum? Can you say anything about the connectedness theorems in that case?
Yeah, it's a good question that I can't at the moment. Yeah, that's a good question.
All right. So the less serious question is, are you going to actually commission Zhongshu Lin to write a poem about the Chinese remainder theorem? He's an expert on generating AI, type of thing.
Oh, I see. Okay.
Yes. So if you haven't seen it, you should go to the conference website for the recent conference for Dan in Georgia.
Okay.
So Zhongshu Lin commissioned a song, and I think had artificial intelligence write the lyrics and commissioned some rock band to play it, and it's
commissioned as in paid money to a band.
Oh, I don't know if he commissioned. I think he constructed it.
Okay.
Yeah, I don't know. Maybe he played it himself. maybe
Right.
maybe he is a rock musician,
He
but
Right.
definitely put it together though in some form. So
right.
okay.
That's nice. That's
He
nice.
organized putting it together, and it's a yeah. We should have more more rock ballads about our
Right.
mathematical results.
That's right.
Right. Yeah. Sorry, I mean, I know so little about group schemes, so this is probably another stupid question. So now, with Wilbert's proof of generalizing Friedlander-Susskind into Noetherian basis, so if I want to okay, so if I look at finitely generated modules over a finite fat group scheme over a Noetherian base, is that an FTC?
Yeah, so I always have required that I think usually the definition is it has to be over a field.
Over a field, right? I say, yeah.
So I know that there are people thinking about this. I mean, I don't remember exactly which co-authors are on that paper, but I know that, I saw Julia Pevsova give a talk about looking at that category. I don't remember exactly who her co-authors
Yeah,
are.
BBIKP, Barthel, then Benzonian
Yeah.
observer, that one, I
Yeah.
guess.
Yes.
But yeah, but I haven't thought about any categories over
Right,
anything that's not a field in the
right.
non-commutative case.
Yeah, when I first saw that paper, I think I asked Henning if one could try to push the Napanov-Vashaw-Yakimov approach and attack that certification. I think someone told me at some point that it's not an FTC, but I don't really know much about group schemes. Okay. Any more questions, anyone? Right. Okay, let's thank Kent once again. Thank you for your time. Right. We are supposed to have Mark Stefan from Bielefeld next week. So hope to see you there.
Thanks.